Okay. Good morning, children. Today we are doing alkenes. You all know alkenes have molecular formula composition CnH2n, and the first member of alkene, N starts with 2, C2H4. C2H4 is CH2 double bond CH2. The next higher homologue, it is C3H6, which is like this, CH3 CH double bond CH2. The next higher homologue is C4H8, which is CH3 CH2 CH double bond CH2, and so on. Okay, now coming to the structure of the simplest alkene. Structure of simplest alkene. In alkene, this carbon is sp2 hybridized. This carbon also is sp2 hybridized. So I am drawing the orbital diagram of ethene. Orbital diagram of ethene. So carbon, this carbon. So sp2 hybridized carbon. So this is one sp2, this is another sp2, smaller lobe I am not drawing, this is another sp2. So this is 3 on this carbon, same on this carbon atom also. This is one sp2, this is another sp2, this is another sp2, and this sp2, it overlaps with 1s of hydrogen, 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 and because the 2 electrons paired up. So in this way, this sigma bonds are formed. This sigma bond we can call it as sp2 1s sigma bond. This is also same thing. This one is sp2 sigma bond. So far what we have got is we have got this one, and in case of sp2 hybridization, one pz remain unhybridized. So that pz I am taking it now, and that pz is perpendicular to this plane. But the pz is perpendicular to this plane, so that I am drawing it here like this. So this is a pz. This is not hybrid orbital, it is pure atomic orbital. This pz, and this is also pz. And this pz and this pz overlap sidewise laterally, that we represent it like this. And pi bond is formed. And this pi bond or the pi electron cloud that we can show it like this. So the pi electron cloud this is for this portion, and another pi electron cloud will be below it. So this is ethene planar molecule with this pi electron cloud. Now one thing let us discuss here is that why conformation is not possible in case of alkene. You know that conformation is possible in case of alkanes. It is not possible because you see here carbon-carbon free rotation is not possible. If we try to rotate this carbon-carbon, this overlap will be lost. This overlap will be lost means pi bond will break. So because of a restricted carbon-carbon free rotation in alkenes, conformation is not possible. Okay, now one more thing let me tell you here is that alkenes, since it has a pi cloud, so this substance, it is rich in electron. Alkenes are rich in electron, and species which are rich in electron, they are called nucleophile. So in chemical reaction, we'll see that this alkene will behave as nucleophile. Okay, now as far as isomerism is concerned, alkene will show position isomerism. So let me draw the position isomerism. Please. Suppose C4H8, you are asked to draw the position isomer of C4H8. C4H8 position isomer you are asked to draw. So one isomer is this one itself, and another isomer will be, suppose we make the double bond now in another position, we make it here. So CH3, C8, double bond CH, CH3. So you see, this one also is C4H8, this one also is C4H8. So these two are position isomers, and IUPAC name of this compound will be but 1-ene, and the IUPAC name of this one will be but 2-ene. So these two are position isomer. You can easily make it out that in case of this one, ethene position isomer is not possible. Even in this case, you will see position isomerism is not possible. So butene has two position isomer, and more higher alkenes, then butene will also have position isomerism. Okay, another type of isomerism which will be there in case of alkene, we have already discussed that. Another type of isomerism in alkene is geometrical isomerism. Geometrical isomerism and geometrical isomerism. So some example of geometrical isomerism I am giving it here. Geometrical isomerism suppose here we have A, and here also we have A, we have B, we have B. You know, if same group is on same side of double bond, then it is called cis isomer, and the trans form of this will be if same group is on the opposite side of double bond, then it is called trans isomer. So what we have seen here is that suppose a molecule of composition C2, A2, B2, molecule of composition C2, A2, B2 will have geometrical isomerism. Okay. So these two are isomers, geometrical isomers. Let me also quickly tell the condition for geometrical isomerism. Okay, this also we had discussed it before. Two conditions are very important for geometrical isomerism to take place. Number one, there has to be carbon-carbon double bond in the molecule. There has to be carbon-carbon double bond. If there is carbon-carbon single bond, it will not happen. If there is carbon-carbon triple bond, it will not happen. There has to be carbon-carbon double bond. And second condition is that each of the two groups attached to doubly bonded carbon, I mean, I am talking of these two groups, this two has to be different. If it is A here, if here also it is A, geometrical isomerism will not take place. This two has to be different. Then only geometrical isomerism will arise. So, we can write here is doubly bonded carbon must be attached to two different groups. So this condition has to be fulfilled. Okay. Now, one physical property that arises due to geometrical isomerism, the trans isomer will be having dipole moment. Dipole moment, we represent it by mu. Dipole moment will be 0. Trans isomer. Whereas cis isomer will have a dipole moment, it will have some dipole moment. That is, cis isomer or cis compound will be polar in nature. This you have to remember, because it has a dipole moment and trans will not have dipole moment. Dipole moment of trans is 0, so it is non-polar, it is polar. Now I am giving you a particular example of alkene having geometrical isomerism. Say these two compounds so this is transform, and this one cis form. So this is trans. You can see if you name this compound that it is trans but 2-ene, the name of this compound, and this is cis but 2-ene. Okay, now an important question can come here. Between these two compounds, boiling point of trans is less. Boiling point of trans it is less, and boiling point of cis it is more. So a question can come, explain why boiling point of cis isomer is more than the trans isomer. So this can be easily answered or explained in this way. Since it is carbon halogen and halogen is more electronegative, so the bond moment for this bond will be this vector, and the bond moment for this bond will be this vector, and these two vectors will add up, and it will have a dipole moment. Whereas in this case, the bond moment for this one will be this. It is always from positive to negative. And the bond moment for this one will be this. And these two bond moments, since they are in opposite direction, will naturally cancel out. And dipole moment will be 0. Now, since this is having a dipole moment, since this is a polar substance, here there is stronger dipole force of attraction. There will be stronger dipole force of attraction, and that's why it will have higher boiling point. On the other hand, here since it is non-polar, dipole force is not there, so that's why it has less boiling point. Okay, now children, after this let us take up this case, general methods of preparation of alkenes. How can we prepare alkenes? Because alkenes are also good fuels. Okay, they are also hydrocarbons, so we should know how we can prepare them, because they have a lot of important uses. Okay, now first method, is from alkynes. From alkynes, we can prepare alkenes. So I'm writing the equation here. Suppose the CH3, C triple bond, C CH3. Suppose this is an alkyne. Now, if we treat with a substance called palladized charcoal. Palladized charcoal. Palladized charcoal, in palladium there is hydrogen is present. In palladized charcoal, hydrogen is present. So that hydrogen will be added up here. And we will get this compound. So So hydrogen gets added here, hydrogen gets added here, triple bond becomes double bond. So, and we get in this reaction, we get cis variety we get. And there is another way to carry out this process. On the other hand, if we treat sodium in liquid ammonia, ammonia is normally gas, but it can be liquefied. And if we add sodium in liquid ammonia, then we will get hydrogen gas. That hydrogen gas will be added here, and in that case, we get trans variety of this product. We get trans variety. So this is one way of preparing alkenes. Second method is from halo compounds. From halo compounds also we can prepare alkenes. Okay, one example is, suppose we have this compound. Suppose we have here chlorine, and all these are hydrogen. So this is a halo compound. So now, if these halo compounds are treated with alcoholic KOH, means KOH is solid. So we are dissolving solid KOH in alcohol. That's called alcoholic KOH. So when this halo compound is treated with alcoholic KOH, what happens? There occurs elimination reaction, and this HCl unit comes out, gets removed. This KOH pulls, we can think in this way, pulls this HCl. So this HCl comes out, and a double bond gets created here. So the product will be H, double bond C, H. So this one will be formed plus side product HCl. So in this way, alkene results. Now, one thing, this reaction is also known as dehydrohalogenation. Dehydrohalogenation, because here halogen acid is removed. Since halogen acid is removed, it is called dehydrohalogenation. So now let me give one more example of this type. Suppose we have CH3, CH, Cl, CH3. Suppose this is a halo compound, and here if we treat with alcoholic KOH, then what will happen is this Cl will go out, and adjacent hydrogen, will go out. So the alkene that will be formed here will be CH3, the CH, double bond H, this plus HCl. So alkene is formed. Now, the third way that we can prepare is third method of preparation of alkene. It is from dihalo compounds. From dihalo halo compounds. Dihalo compounds like this compound, say carbon, carbon, so you see there are two halogen atoms here, so it's a dihalogen compound, and this is actually a vicinal dihalide. It is vicinal dihalide. Usually here vicinal dihalide is required. Vicinal dihalide means if the two halogen atoms are on adjacent carbon, then it is vicinal dihalide. Now the two halogen can also be like this. Two halogen can also be like this. It is also a dihalogen compound, but it is not vicinal. The two halogen are attached to the same carbon, and that is called geminal. It is geminal, and this one is vicinal. And for the preparation of alkene, we require vicinal dihalide. So here what happens, if it is filled with zinc dust, finely divided zinc, and if it is heated, then what happens is this halogen, they come out. They haven't come out, and we have this compound. And since halogen is getting removed, this process is called, or this is known as is dehalogenation. Sorry, yes, dehalogenation. Previously it was dehydrohalogenation. So this is a third way, and another way is we can also get alkene from alcohol. From alcohols, so suppose we have, say here, we take an alcohol. This is ethyl alcohol, whose IUPAC name is ethanol. And if alcohols are treated with concentrated sulfuric acid, at a temperature of around 443 Kelvin, at 443 Kelvin temperature, then this 8OH, which is water, this water gets lost. Why water gets lost here? Because concentrated sulfuric acid is a very good dehydrating agent. It removes water molecule. And then what this will result. So children, this is about preparation of alkenes. Okay, so this much for now. You will be having the next video that will be coming up. That will be on chemical and physical property of alkenes. So till then, have a good day. Bye bye.